for virology, ELISA for virology, and lateral flow assays. Lateral flow assays are probably better known as rapid detection tests or RDTs. These are the things we use for testing things like HIV, even pregnancy on the bench or on the table or at the clinic. In the morning, we were talking about measles, mumps, and rubella. And we kept repeating that some of the tests you can do actually for all the three viruses is detection of IgM and IgG antibodies. And the leading method for such kind of detection is usually ELISA. So it's a method that is probably the most commonly used for diagnosis of ELISA of viral diseases. So it's important to understand how it works. The outline for today's presentation is, as you can see on the screen. We are going to talk about the types of ELISA. There are 4 main types. We'll talk about applications, and then we will set up an ELISA using dengue as an example. I don't know if you guys have covered dengue. Let me know in the chat if you have covered dengue. Even if you haven't, it's just a placeholder for any other virus or any other condition. And for this, we will go through the processes of identifying the correct tests, because there are many ELISAs. How do you know which one to choose? Right now, if you go into a shop to buy a dengue ELISA kit, how do you know which one to pick? How do you come up with a standard operating procedure? Because for every assay in the lab, you need an SOP to make sure everybody does the same thing and the right thing always. Also, how do you validate that assay? That assay that you've selected, how do you confirm that it's going to give you valid results? And how do you run the test? What are the potential errors or pitfalls that you're likely to come across? The types of ELISA are listed here: direct ELISA, indirect, sandwich, and competitive. These 3 diagrams illustrate the first 3. You can see for direct ELISA here, if the flat surface is what we call let's say the well, which is usually a fixed surface anyway, and you have put there an antibody of antigen of, say, HIV, or say your sample, you're looking for an antigen of HIV or any other disease, you can use a known antibody, like the primary antibody you're seeing here, to detect this antigen, to detect if the sample has this antigen. So basically you have a well, and I'll show you what a well is, a microtiter well, a small well of a sample. You put in your sample, which has an antigen. Say the antigen is HIV, you're looking for an HIV protein, and then, or dengue protein, say NS1 for dengue, and you use a known antibody. So you know this antibody will bind to the antigen of interest. So you mix the two, incubate, and this antibody is conjugated to a compound which reacts with a substrate to produce light, or produce a color that is not light, but a color that is visible. So this is the detection mechanism that we use across all the 3. What changes is what you are detecting and the mechanism for detection. I had asked a question. Let me see if you have covered dengue. I think you have, so this is timely. The indirect assay, instead of having the sample at the bottom or the sample fixed to the plate, you buy a plate or you prepare a plate already fixed with an antigen, of a known antigen. So maybe an antigen for HIV, or in this case, an antigen with dengue, NS1, of dengue NS1. And then you want to find out if the sample you have, the sample you are testing, or the patient you want to test has antibodies against dengue. So this primary antibody is from the patient. And what happens is that you have the plate or this surface, which is already primed with the antigen, and you add a sample, and the sample, if it has antibodies, they will bind to the antigen that is already known. So of course, the blood sample will have other antibodies, but those antibodies will not bind to this antigen because this antigen is specific. And then you have the detection mechanism which uses a secondary antibody. This secondary antibody will bind to the primary antibody. And what we usually do is probably get something like a anti-human IgG. So because you expect that the patient sample will have human IgG, which binds to this antigen that you've already placed in the plates, you want to see if any human IgG has been bound. And for you to detect human IgG, you need an anti-human IgG antibody. And this anti-human IgG could be from even a rabbit or whatever. It's conjugated, and that means if you add a substrate, you will see a color change, and you can measure that color change. So you are using the antigen as a bait to bind the antibody of interest, and then you're using a secondary antibody to detect if the primary antibody is present with a color change, of course. And then you can also have a sandwich. Here you have a primary antibody on the surface of the plate. Then you add your blood sample, which could have, say, an antigen of interest. And then you have a secondary antibody that can, actually this would be called now the primary antibody that can bind to your antigen. And you detect this combination using your secondary antibody that can then produce a color change. You can see in this situation, you can have a capture antibody that is already bound to an antigen on the plate and use that to detect antibodies, or you can have the capture antibody and use it to detect an antigen, although most of the time it's used to detect this primary antibody. The different ELISA methods will have different advantages. This one is not very specific, but it is easier to do. And a lot of the ELISAs that you're going to use are indirect. There are some that are sandwich, and there are a few that are competitive. The most common one is usually the indirect ELISA. In terms of competitive ELISA, this is a bit different. What happens is that if, for example, you want to detect this antibody, primary antibody, say antibody for HIV, you already have another HIV antibody whose concentration you know. So when you mix your known concentration antibody with the patient sample, if there is any patient sample antibody, it will compete with your known antibody, the one that you know the concentration. So the more the patient antibody, the more the competition. And at the end of the day, you can use that to quantify the antibodies in the sample. So we won't discuss competitive ELISAs much. I can encourage you to check that. I want to focus on especially indirect so that we can learn how the ELISA works. If we try to teach you everything, we might get mixed up. So this is what I've been referring to as a well. It's a microtiter plate with small wells. This is about 300 microliters, which is about 1/3 of an ml. And you can see there are several strips. I think there are 12 by 8. And each of these is, say, for an indirect ELISA, it would be coated with something, say an antibody or an antigen, or it could be blank and then you have to coat it yourself, especially if you're developing this in the lab or the kit is designed like that. But coating is not difficult. Just there's a what we call nitrocellulose membrane here that will bind the protein. Sorry, my voice is disappearing. I think I've spoken too much today. So this is what we are referring to when we talk about a plate, sio sahani ya githeri, or a well. This is a 96 well plate, 96 well microtiter plate. These are called microtiters. Okay, because they take microliters. So I'll show you a video. Maybe this will allow me to recover also. At this point, I think I'll share my entire screen. It will be easier to move on from here.
or ELISA, is a commonly used format for the enzyme-linked immunosorbent. ELISA immunosorbent assay, or ELISA, is a commonly used format for serologic testing. The purpose of this animation is to explain how this test works. ELISA serologies are usually done in multi-well microtiter plates so that dilutions of serum can be easily prepared and tested. To better understand how this assay is done, let's take a closer look at what happens in one of the wells of this assay plate. To perform the assay, the wells of the plate are coated with the antigen of interest. For commercial tests, this would be done by the manufacturer of the assay. To begin testing, the wells are filled with dilutions of the patient's serum. If antibodies against the antigen are present, they will bind to the antigen fixed to the bottom of the wells. But only antigen-specific antibodies will bind to the wells. The wells are then washed out to remove all unbound antibodies. Next, a solution of an animal antibody against human antibodies is added. This second antibody is covalently conjugated to an enzyme. The wells are washed again, this time to remove any unbound enzyme-conjugated antibody. Finally, a solution of a colorogenic enzyme substrate is added. The interaction of the substrate with the enzyme on the second antibody generates visible color. The development of color in the wells with a specific antibody can be seen with the naked eye or quantified with an electronic plate reader. The reaction is less intense as the serum is diluted and the amount of antibody captured in the wells decreases. The titer is the highest dilution with definite color development.
Okay, so just I would call that a teaser. We'll be looking at one or two more videos depending on how much time we have. This would have been easier if you were actually doing it on the bench, but because of the numbers, that is not possible. But you'll still get a good idea and understand it, especially if you need to use it for your patients. So this is again to further explain the setup. On the left, you have an indirect ELISA. This on the bottom, at the bottom, is a plate or a well, which is already, you are buying this from the manufacturer already with the antigen fixed on that plate. And what you're interested in detecting is the primary antibody. So in this case, you will add the patient blood, which if it has antibodies, they will bind to the antigen. And you know the antigen says it's for HIV or for dengue, you already know that. But you don't know if the patient blood has antibodies. So if the patient sample has antibodies, they will bind to the antigen. And then the detector antibody, which is the secondary conjugated antibody, will bind to any primary or any target antibodies in there that are in the plate. And you've seen after every step you wash, so that if you have this antigen bound here, you add the sample, you incubate it, and then you wash. After you wash, if there are any antibodies that are not being bound, they will be washed off. But those that have been bound to the antigen, they'll remain. And then now you add your conjugate, incubate again, your conjugated antibody, you incubate again, and wash after that. So usually incubation can be 1 hour, 30 minutes, you're at 37 degrees Celsius, basically at the body's temperature. And a conjugated antibody is really an antibody that is able to bind the human antibody here. So usually it's an anti-IgG, anti-human IgG, but it has a conjugate, meaning it is connected to a chemical, which when it's reacted with another substrate or another chemical, will produce a light, a color. And you can see here some of the conjugates that we use, like biotin, and some of the substrate we use, like streptavidin. You don't need to get so much into those. Just know that it is a substrate that can produce light when it reacts with the conjugate. Color, why do I keep saying light? Visible, color that is within the visible spectrum. Now, in the second, so this is an indirect ELISA. In the second one, the first one is for detecting antibody. In the second one, you have the well lined with antibodies, which are called the capture antibody, this one. And you want to see if your sample has an antigen. So you add this target protein, could be the antigen, say, and it can also be an antibody, by the way. But in this case, I was just showing you a separate way of detecting antibody and antigen. So this could be, say, NS1 antigen of the dengue. And so if it binds to the capture antibody, which is specific to this NS1, then you have another antibody that can bind this antigen, which means you have two antibodies binding to the same antigen, making it more specific. So if it is difficult for two antibodies to bind to one protein non-specifically, meaning binding to another antibody which is not the target, another antigen which is not the target. So in this case, you have two opportunities to check specificity. And so this is more likely to have very good specificity, to be specific to the particular target. And then, of course, there's a detection mechanism with this conjugated detection antibody reacting with a substrate. So really, that is really the simple end of it. You have antibodies and antigens interacting, and you have a way of detecting that interaction. So for dengue, this is just like a background. You know it's a flavivirus transmitted by Aedes mosquito. The target for ELISA can be IgG antibodies, can be IgM, can be NS1 antigen. So for now, let's select IgG antibodies for illustration. You can also have ELISA for NS1 antigen. In fact, when you're doing ELISA for dengue, it's good to do for all the three at once, or using either the same kit or different kits. Most of the time, it's a different kit. To remind you that as a doctor or when you're practicing, you need to think about the specific status of a patient. Remember, many viruses may not necessarily be in blood at the time, or in a sample, or in a patient by the time the patient is coming to you. A good example here is dengue. A patient will start having viremia 3 days, 1 to 2 days before the presentation with fever. You can see fever starts on day 0, but a day or two before that, they already have virus. They won't come to you a day or two and tell you I have virus in blood because they don't have symptoms. But the day they have fever, they have a reason to come to you. So they'll come to you maybe on day 1, day 2, day 3, day 5, day 7, depending on how bad they feel. And if they've had fever for a few days, viremia disappears by day 5. And with viremia disappearing, NS1 antigen, which is part of the virus, also disappears. So if a patient is coming to you on day 3, they tell you I've had fever for the last 3 days, and you're suspecting dengue, what goes in your mind is, if I order IgG, will it give me any information? And if you're ordering IgG on day 3 and it's positive, does that indicate current infection? Maybe, if it is a reinfection, because when there's reinfection, antibodies come up very fast, even IgG. But if it's a primary infection, IgG will be negative. Does that mean that person does not have dengue? No. If IgG is negative, it doesn't mean that person doesn't have dengue. It just means you tested the person too early before IgG could develop. If you're testing IgM on day 2, day 3, and you don't detect it, maybe it's too low, but maybe day 4, day 5, it could be detectable. And you should keep that in mind to know if you're testing the patient in day 3, maybe you need to look for the virus, either NS1 or the PCR or the IgM. And if you happen to look for IgG and you find it, then either you do another IgG later to see if there's a titer that is increasing, or to see if IgG was just there because of a previous exposure or because of a false positive, or what we call cross-reaction. So you need to think through the presentation so that you know which test to do. A good example is HIV. We know P24 antigens will disappear at some point. Initially, they are very high. They come up early in the infection. You do a P24 antigen test, it's positive. But as the body's immune antibodies start coming up, they can mop up all the proteins. So if you test for HIV at 2 years after infection, maybe the person will test negative if you use P24. And that's why most of the tests we used to do combine other tests. They combine antibody and antigen, or the virus itself, because if they're infected, the virus will still be there, even after how many years. So unless they're on treatment, then it may be a bit tricky to find it. So keep this in mind. It's not for you to memorize, it's for you to know that for every infection you're looking for, you need to think through the timing and which markers to look for. When do antibodies come up? When do the virus, when do the viral antigens disappear? And so on. So in this case, we are wondering, you want to set up a dengue. Of course, right now you might just send it to a lab and ask them to test dengue. But now imagine you are running your own lab, or you are the one charged with the duty of determining which dengue test to do. Where do you start? This is a good place to start. Maybe we should just open this and see. Looks like it doesn't want to cooperate with me. Yeah. So this is just PubMed, and you can type here commercial. Commercial means it's already prepared. You can also have in-house. In-house is when you prepare the test yourself. You can get the plates that are blank and then load them with a protein of interest and then use them for testing, but you need to validate, and I'll show you how to validate a test. So commercial dengue ELISA assay. And you just search. And they'll come, several of them. You read through each. Usually I just look at the title first. And then I decide diagnostic accuracy of commercially available immunochromatographic. So these are rapid tests. So if you are looking for rapid tests, this would be interesting. Evaluation of commercial serological assays in Malaysia for detection of anti-Zika. If you're looking for Zika, this would be okay, but that's not what you're looking for. So evaluation of NS1, maybe because I want IgG, I can specify now. Just add here IgG. We don't need to use caps or connectors. I'm looking at the titles now, so don't worry if I scroll too fast. Evaluation of commercial serological assays from Zika. The reason with this, because Zika is flyvirus, they tend to cross-react. That's why it is coming up. If you want to exclude Zika, you can say here, not Zika. If you feel it is crowding your field. But likely it might lock out assays that also tested for Zika as they test for dengue. Comparison of 6 commercial diagnostic tests for detection of dengue. So this is something that you might look at. You click on it, read the abstract, see if it helps you, and I think it looks useful. So open it and see. Does it give you the information you need? And this is telling you that we compared the ability to detect NS1, IgM, IgG among these 3 tests. This is one test by InBios. This is another test by Abcam. These are commercial producers. These are manufacturers. And then there's another test by Euroimmune. And then you read what they did, and then eventually you'll find information that you're looking for, which is here. And I have summarized this. Actually, I think the same paper I used to summarize by coincidence, if I'm not wrong. So you are looking for sensitivity, specificity, and accuracy, including these ones. So now we'll go back to the presentation and you can see this in a much simplified form. So this is how you and you can do that for HIV or for another test. It helps you to reduce the amount of time you have to search for a test. The other thing you can do is to look at existing tests. This is just one of maybe hundreds or dozens of websites that sell kits. It's called Fisher Sci, which I use frequently for my work. And you just come and type here, dengue, IgG, ELISA. This is like a shop. This is like an online shop. And then when you find several kits, you'll find several kits. You can then pick a name of the kit that you like. Maybe you have seen a manufacturer you respect, or you've seen maybe the price is okay. Have I clicked search? Yes, so I think I'm using a lot of RAM. Let me just quit something here. Okay, so we have, maybe you want to use one of these. So you just copy the kit test and then the kit name, and then go back to your, what is it called? PubMed and search. So you can paste it here. Say we had found, we wanted to search this one, anti-dengue IgG Euroimmune. You can paste it here and search. So then it will bring other papers that have, I think I should move these brackets and also maybe the caps. Yeah, so search, still not what I want. Control O, Control X, I'll just open PubMed afresh so that I make sure. So search. So you can see, if you want to see whether there's any publications of this, they'll tell you who has used it, how did it perform, how did it compare with others. So eventually after this process, you're going to have your, you can also do the same with lab compare. You can also call your plug. If Mugambi is your plug for kits, ask him, do you have a dengue kit? Which ones do you use? How much is it? And then take a look at it and see whether it performs properly. Don't just pick a kit because Mugambi is selling it. You need to check online what other people have said about it, what are the challenges with it, and then you can move ahead and validate it. I see some comments in the chat. I'm going to look at it. I'm going to look at the chat, that is. Yeah, I think some of these are not relevant to my class. Inhibiting, okay, yeah, I don't think we need to respond to any of those. So once you have identified the kit or the kits, maybe you have 3, you want to know which one to choose. Look at the accuracy, and I'll show you how to measure accuracy because I know we've been discussing this 2 or 3 times. Sensitivity, specificity, and then technical requirements. Like they might tell you, you need a machine which can read this certain wavelength, maybe 600 nanometers or whatever it is. Make sure that you have that machine. Usually we call it an ELISA reader or a spectrophotometer. The procedure also, is it too long? Maybe it asks you to use 200 microliters of blood and you can only afford 50 microliters. So what do? Cost as well can be limiting. So think through those technical requirements as you read about the kit. So by the time you select the kit, you have looked at these things. You have seen, for example, in the paper that we saw, Abcam, InBios, and Euroimmune, which are brand names for IgG dengue kits. All of them can detect dengue, but at different accuracies. You can see one has 97% sensitivity, another one has 100%, and another one has Euroimmune. But there are trade-offs because the one with 100% sensitivity has a lower specificity compared to the others. This one with the sensitivity and specificity around the same point, and this one has a higher specificity than the others, meaning that if it tells you something is negative, it's not likely to be positive. It is likely to be correct. This one, if it tells you something is positive, then you know it is positive. I mean, you know it is going to detect, it's going to detect all positives, but there's a good chance that some of the positives it will detect are negative, so there'll be false negatives. Basically, it overstates, it exaggerates the positives. Now, I'm going to use the next table to make this easier. What you want to do with validation is to confirm that these numbers, say the manufacturer has told you my kit is 100% sensitive and 90% specific, you want to validate those claims. You don't just believe them. So you test samples, and you can have samples that you already know the results, either because you tested before with a gold standard test. For dengue, a gold standard would be neutralization assays, or you can buy a panel. You can buy a panel from what we call EQA programs, or external quality assurance programs. You tell them, please send me confirmed samples for dengue or for whatever it is that you're looking for. And usually there are a few, even 30 positive and 30 negative are enough for validation or verification. But sometimes if you want to change some, maybe the volume or the duration of incubation, you may want to do 200 or more, or 100 at least. So you compare with a gold standard. A gold standard is that test that is comparable with what you're doing. For example, right now we are looking for IgG. You cannot compare IgG with PCR because PCR will detect the virus, yet IgG is detecting antibodies. So the gold standard for antibody detection for dengue is what? Neutralization assays, because neutralization assays will detect antibodies. So be careful when you're choosing the gold standard. Make sure you're looking at the same thing. Eventually, by testing these samples, you will calculate the accuracy, sensitivity, specificity, positive predictive value, and negative predictive value. Actually, in the next example, I have used, and maybe to avoid confusion, I can change here. I have used the number of samples that are positive to be 100. This is just arbitrary, it can be fewer or more. And then the negatives to be 50. And this is really the table, we call it a contingency table that we use to calculate those things. And I'm going to ask you to get a pen and paper so that you can calculate. And the positive, the non-results, the gold standard is this one. You can say, for example, you have 100 positive results by the gold standard. And you want to see if your new assay, the one you have bought, can detect this 100. And yet, when you test, the new test only detects 90 correctly. So it says 90 are positive and 10 are negative. Yet you know they are positive. So what is the sensitivity there? Anybody? You have 100 samples that are positive according to your gold standard. Your test or the new test says 90% are positive. 90 are positive and 10 are negative. So the sensitivity will be the ability to detect out of these 100 that are, let me see, yes, 90% is correct. How do we arrive at that? You take the true positives over true positives plus false negatives, which is this 100. This is the false negative because you know it is positive, but your test has said it is negative. So that comes to 90%. So your sensitivity is 90%. Now at the same time, and you run this test simultaneously, you have 50 that you know are negative according to the gold standard. When you test with your new assay, it tells you that 45 are negative. So you know it has gotten 45 correctly. That 45 are really negative according to your test, but 5 are deemed to be positive. So what this new test has done is tell you that out of the 50 that you knew were negative, 5 are wrongly positive, are wrongly classified as positive, and that's why they're called false positives. So what is the specificity here? How do you calculate specificity? Specificity so you take true negative, which is 45%, over false positive plus true negative, which is 50, and that gives you 45 over 50, which is 90%. Okay. They might look the same, but they're actually different. Now, the others are what we call positive predictive value. And the positive predictive value is talking about this test has told you that 95 samples are positive. But how many of these are actually positive? You see, the true positives are 90, the true and false positives altogether are 95. So that accuracy or the positive predictive value becomes around 95%, which is 90 over 95. 90 over 95 comes to 94.7. For the negative predictive value, this test has told you in total, out of the 150 that it tested, it told you that 10 were falsely negative and 45 were true negative. So in total, 55 came out negative. So if you get 55 tests out of, that are negative, how many of those are likely to be correct? And you can see the true negatives is 45 and the total is 55. So 45 out of 55 are true negatives, and that gives you a negative predictive value of 82%, which is a bit low. So it tells you the specificity, the negative predictive value for this kit is not as good as the positive predictive value. If a kit has bad, or let's say not so, this is not so bad actually, 80 is very good, but it's low, it means if somebody tests negative, you may want to repeat and see with a more sensitive test that they are not, you have not missed. You can see here you would have missed 10 people who are misclassified. You can see they are called false negatives, yet they are supposed to be positive. Now, the final measure is this one, accuracy. And the accuracy is looking at, out of all the 150, how many were correctly categorized. And the ones that are correctly categorized are the true positives and the true negatives. So the idea is you get the true positives plus the true negatives, that's 135, over the total number tested, which is 150. And that gives you 90%. So 135 over 150 is 90%. So the accuracy of this test is 90%. I hope that is now making sense. We've been talking about sensitivity and specificity for a while. I hope you have now you have at least a resource you can use to make sure you understand these terminologies. They're not very difficult, but they can confuse some people. So after you, maybe now I should just remove this screen sharing and use the slide sharing. So after you identify your kit, your assay, you decided, let me use Euroimmune. This is actually an exercise I did, and I selected Euroimmune, which I'm currently using to test my samples. I've actually finished, but yeah. The first thing you see here is to look at the procedure summary in the kit. The kit comes with an insert, and you read it. If it's not in the kit, you can download it. So just read it and see what it tells you. In this case, it was telling us that the well is already it's already coated. Yes, coating is the word. It's already coated with the capture antigens. So these are dengue antigens or dengue proteins. And so when you insert your sample, if there are any antibodies in the sample, they will bind to these dengue proteins. And then you wash off and add your conjugated antibody, which will bind to the patient's antibodies now. And when you add your substrate in the next step, the color product will be seen and can be quantified using a machine. Remember, after every step you wash, except this one. You don't wash between, because here you have capture antigens, so you add your sample, incubate, and then wash. After you wash, you add your conjugated antibody, incubate, this is usually for about an hour at 7 degrees, then you wash. Then you add your substrate, which produces a color product, and at that point you don't need to wash, you read with a machine. I'll show you, I think, how the machine looks like. Assay protocol has to be developed, and you need to think through the entire process of sample collection. How do you pipette at each step, how much volume, how long, and all that. And then how do you read, at what wavelength? You need to tell you to read between maybe 400 and 600 nanometers. And then how do you interpret? So, and once you understand these steps, then you know where things can go wrong. The first thing is your sample, and most of the time you're looking for antibodies in blood, but it's not actually blood, it's not whole blood. You can look for antibodies whole blood, but there'll be a lot of noise and background because of proteins and non-specific binding. You can use serum or plasma. You can see the difference here between serum and plasma. When you're collecting serum, you don't use an anticoagulant. You use an empty tube. It could be this red topped or this yellow one. The yellow one has something we call a serum separator gel, which when you spin, the cells go below the gel and the serum comes up. But this other one, there is no separator, so you just pipette the serum out once you centrifuge. But you can see the clot here picks all the blood, what is it called? The red blood cells, the white blood cells, and even some of the proteins like fibrin that are used up in clotting. The plasma, there's no clotting. So you'll find your blood cells, you'll find a buffy coat in between here, and you find your plasma at the top. You can use either of these to test for antibodies. And you can see for plasma, you use tubes with anticoagulants, like this one here with heparin, and another one here with the, you guys are familiar with the purple one for that has EDTA. This is your ELISA plate. And as you saw before, maybe in the video, you can actually use some of the strips. Maybe you only have 10 samples to test, but your plate has 96 samples. So you take a strip, maybe 2 strips, because you also need extra wells for controls, and you map it. So depending on the assay, you might find that it requires to have standards, negative controls, duplicates, some other control, positive control, and you can also have your own non-sample. You can add there and say, because this sample I have, for example, somebody who gave me a sample, their own sample, because they had antibodies for Zika. I have antibodies, say, for yellow fever, and I can use that because I got vaccinated twice. I know I have antibodies that have confirmed with a cross-reaction. So I want to see, will this kit detect? Because I already have this sample that I know. You can include it there as a control. But you also have controls that come with the manufacturer's kit. And once you put the controls, you can also then add your samples. This is sample 1, sample 2, sample 3, all the way to sample 13. And some kits, manufacturers say you test this in duplicate or in triplicate. So if it is duplicate, then you add sample 1 to 8, then sample 1 to 8, that's a duplicate. If it's a triplicate, then you add another row for sample 1 to 8. And then for the next row, you take the next 3, and so on. If you don't need to use the extra wells, you remove them so that they're not contaminated, and you only pick the ones that you're using, because you can spare the others for the next test, for future use. The stepwise is like, as you can see here, for the kit we selected, and this is really just to walk you through the steps. The first one is to prepare all the reagents, your samples, and your controls. You make sure that everything is on the bench. Kama ilikuwa kwa freezer, you get it out. It thaws, or it comes to room temperature, and so that the antibodies, you don't have anything in solid form or something that cannot react with the others. I see some questions here, but I think we've already answered them. And your first step to add to the well is to add your standards, your controls, or your samples. So each well, you only add one thing. So maybe the first well, you put a standard. A standard is what guides the machine as to how to measure the rest of the optical densities. And then you can add a positive control in a different well, a negative control in a different well. If you contaminate the negative control with your positive control, then you'll have some problems. So when you're pipetting, you need to be very careful. And then you can see an incubation here at 37 degrees for 1 hour. This means you're incubating the wells with the antibody. This can be with the sample. The sample may have antibody or not. So during incubation, if there's an antibody, it will bind. And then during your wash, and you wash 3, actually sometimes 4 times, if there are any free antibodies, and free antibodies will be there because your blood has so many antibodies, only that they will not bind to dengue unless they are dengue antibodies. So they'll be washed off, and only those that are bound will remain. So you add your conjugated antibody, which will bind to the antibody that you want to detect. So as I gave you an example, that this could be an anti-human IgG, which binds the IgG antibody that you're interested. So it's like an antibody to the IgG. And once it binds, you wash, and if there is no, if there was no the primary antibody was not there in the first place, everything will be washed out. But if there was some, depending on the quantity, some will be retained after washing. So then you add your substrate, and the substrate will produce a color. Sometimes you can actually see the color very well with your naked eyes, but you cannot quantify the optical density. You have to use a machine to quantify. And then you stop the reaction with an acid. And then after you stop the reaction, you don't wash, you go and read using an optical reader. And when you read, it will give you numbers like this. It will give you an Excel sheet. It will tell you the substrate had these absorbance, the negative control. And if you look carefully, you can see the positive control has a higher absorbance than the negative control, and so on and so forth. So the question is, how do you know if sample 1 with this absorbance is positive or negative? How do you interpret these results? Because they'll just be numbers. You go to the next step, which is looking at the kit insert, which will have the cutoffs. You don't have to cram this, please. Each kit will have its own different numbers. And you can see this one tells you negative control absorbance should be from 0.2 to the cutoff. And the cutoff is 0.1 to 1.3. So if for some reason you contaminated your negative control, it will be above this. And so you know you're in trouble. And maybe you have to repeat. Because contamination is not good. The positive control you can see is greater than cutoff. So anything greater than 1.3. So you know for once, anything that has an absorbance value greater than the cutoff will be positive. But it has to be greater than cutoff by at least 10%. So you can look at the samples and look at the cutoffs and decide, these ones, are they okay? Because you are told the substrate should be below 1, and you see it is below. The negative control should be below 0.5. It is, you can see the negative control here is supposed to be below cutoff, and your cutoff here is more than the negative control. So the what you need to determine with these ones are whether they are valid or not. If they are valid, then you proceed. And the validity determines on what you are given here. You don't have to cram it. The next lot is then different samples. Now I've just categorized them for you to understand. You can see the first one is, they are fairly high values. If you compare with the positive control, these ones are actually around the same. And so we call them positive because they are more than 10%, the upper cutoff, which is good, clearly positive. Then you can also have negative. You can see these ones are below the cutoff, so no worries there. But you have others that are borderline. So what do? These ones are not more than 10% higher than the cutoff. So this become a bit tricky. And then the best thing to do here is, any ideas? What do you do with the borderline assays? I've been speaking for too long. I don't know why today I feel like I've been talking in a rush, but there's still time to catch up. We're about to finish, don't worry. So what do you do with the borderline? Anybody? Retest. Ria Patel, you are right. You retest, you repeat. Or you can even test with a different assay. And you can see there's another batch here that is false negative. Maybe question here is what happened because it is too low. If the sample is too low, maybe you didn't add your sample into the well. You thought you added, but you didn't. So there could be issues. And yeah, there are others here that are negative and clearly positive. So that's how you interpret. Now, do not cram these values on the right, this absorbance. This is not, it's going to change for every kit. This is just to walk you through what you do so that you remember. So you can see by the time a lab is telling you that the patient is positive for dengue, they have gone through so many steps. So in your mind, you should be worried when there's a test that is not consistent or a result that is not consistent with what you expect. Then you need to think through what could have gone wrong. Did I collect the right sample? Did the labs do the right test? Was the sample collected at the right time? As I said, you could be looking for IgG, yet the patient has only had a fever for 1 day. They may not have IgG unless they were exposed to dengue before. So things like that. So these pitfalls are the kind of things that might give you false results. And assay selection is the first. If you don't collect the right, you don't select the right assay, then you'll be in trouble. And we've seen some people testing, say, blood on an assay that has not been validated for blood. Maybe it was for urine, and you're surprised when you get funny results. You need to validate. If you want to use it for a different sample, you need to validate afresh with that sample. Because sometimes you have to modify, say, the incubation period, the incubation temperature, the volumes of the sample. Some kits require 10 microliters of the sample, which is just very tiny. Some kits will require 100 microliters of the sample, and maybe you only have 5 microliters, and you want to test so many things. So keep that in mind, because you might find yourself stuck. But sometimes when you find your very little sample, you can top up with the PBS, which is basically something we call phosphate buffered saline. It's basically safe water for biological processes. This is another common issue where you don't store your reagents properly. Say, for example, you have imported reagents, and then they come to the pot and they're delayed there for 2 weeks. If they're not stored in the right place, say a cooler, a cold room, you might get reagents that are already spoiled. And that's why for every batch of reagents you receive in the lab, you must test, you validate with the previous one. So you receive a new kit, you run a few controls and see that the kit is working. Sample collection might also go wrong if you use the wrong container, like I showed you what to use. If you, for example, are testing reagents, samples, and the sample collection was bad, then you might have issues. A good example is when you have lysis. So if you have hemolysis, you'll have a lot of background. So you may have very high optical densities, yet the sample is negative. Reagent preparation and pipetting errors. So maybe you are told to add, instead of, you're adding 10 microliters of the antibody, but you add 100 or double. What happens is that there may be non-specific binding, which gives you also the wrong results. Sometimes when you're pipetting, you might skip to add a sample. Maybe you're only adding 10 microliters of your sample and you forget. You skip that well. You think you have added, but you have not. That gives you a false negative. Maybe that sample was positive, but the well is empty, meaning you didn't add any. It will not be empty because you'll already have things inside, but you didn't add the sample itself. So there's nothing you're really measuring. You're measuring an empty well. If the incubation time is too long, then there'll be a lot of non-specific binding. If the washing step is too short, you'll have a lot of background because you're not washing away all the antibodies that are not bound. And if you wash too much, you'll wash everything. And that's why we optimize. You see, if I wash for 5 times, is it okay? There's a time when COVID was just beginning, we had a new kit, we washed for 5 times, and almost everything was positive. And that kit was using a lot of serum. It was using like 100. So what we did is we started washing 10 times. And fortunately, there's a machine that does automated washing. You don't have to do it yourself, but in some labs, you have to do it yourself. So after washing 10 times, we realized we were getting better results. So those are some of the things you optimize. Optimization meaning you are you're tweaking the processes to make your test work better. You could also have a delay in reading. So maybe you've already added your color reagent and the stopper, you see the plates, then you're about to go and read it, and then maybe the machine is not working. You find that the reader, the optical reader or the ELISA reader is not working. What do? That happened to me once, by the way. You have to test the reader before you start the PCR, the ELISA. Test it, make sure it's working. Don't assume because you used it yesterday, today it's still working. Because you can imagine this decays. This is fluorescence, or this dye, this substrate will decay, and within an hour, if you don't read it, then the accuracy will be lost. And then the interpretation can also go wrong. You saw where we were looking at the levels, that if it is above this or below this, you need to conclude that it is, say, positive or negative or invalid. So interpretation is also an area where you need to be careful, and also other pathogen factors. And one of the most notorious things about dengue is cross-reactivity. If you have antibodies for dengue, you might test positive for yellow fever, for Zika, for West Nile, and what have you. And that's why we pick the positive tests and further test them, say, for dengue and S1, or for neutralization assays. And with neutralization assays, we have some accuracy. Even with neutralization assays, you can say this is dengue virus 1, or dengue type 2, or dengue type 3. So you need to keep that in mind so that you understand the pathogen, not just the test. If you don't understand the pathogen very well, you might make the wrong interpretations. I think it's time for a short video again as we shift to lateral flow assays, which is just 2 or 3 more slides. And I can let you guys go and enjoy your weekend. Any questions? Let me check the chat. What reagent is used in washing during the ELISA? You can actually use water. The problem with tap water is that if it's contaminated, you have issues. So we use, there's a particular type of water we use that is like PBS, like is phosphate. It's buffered so the pH is okay. It does not interfere with the antibodies. It doesn't interfere with the because remember, antibodies will bind differently depending on the pH and the salt, the ion level of salt in the water or in whatever you're using. So we use phosphate buffered saline to wash. And sometimes the kit comes with its own washing buffer. So that's what you use. Because if you change the conditions, then some antibodies might detach and then you have false negatives. Hi, Doc. To avoid pipetting errors, can the system scan and verify that all wells contain? Well, it's difficult to do that because by the time you are washing, really, and some of the volumes are so low, you need a very accurate scanner. So what some people have done is they color code so that you know when you've added a certain reagent, but still that's not very, it doesn't cut across. So you have to be careful really. You arrange your samples in such a way that if you forget to add something, you will know. And that comes with experience. Where do we add animal serum specifically? Animal serum, I'm not sure I understand your question, Ashley, please retake it. What do borderlines, what do we do? Oh, so when a borderline, it means it's just above the cutoff, but it's not, the margin is not big enough for you to say it's positive. So what you do is you repeat and see, and then you can take the average of the duplicated test. Kumbe kuna sandwich ELISA. I think this guy is still thinking about lunch. His name, Stories Ajaba, might mean is also on something else. Can a patient's blood sample or blood type affect the reagent for testing? Well, it depends on what you're testing for. If you're testing for dengue and antibodies or other viruses, no, it will not. But if you're looking for blood group and those other things, of course, it will. They have antibodies complementary to human antibodies. Yes. So basically, if I take human blood and I inject it to a rabbit, it will form anti-human IgG. And you can actually take that and purify it. But usually there are other ways of producing monoclonal antibodies even against human IgG. Are the wells usable? No, they are not, because remember, the well is coated with say an antigen or an antibody. So once the antibody is bound, then that's it. Maybe you can use a negative one. I've never tried to think about that, but I wouldn't try it, because when you get a test, the result you may not know. But generally, we don't use. Hello, Doc, kindly elaborate the difference between capture and antigen indirect assay. Well, there's no antigen assay. There's no assay called a capture assay, but I'll go through the different types once again. Mugambi, can you use normal saline to wash? If the normal saline is phosphate buffered, basically it ensures that the pH is okay and there's no excess salt, but not just normal saline. Because when you put in a lot of salt, the antibody, the binding, the avidity of the antibody antigen complex will be affected. What was the difference between positive and negative control? A positive control is positive, a negative control is negative. And you need both, so that you know, you get the cutoffs. Is the antigen that is used for coating the well able to cover various serotypes of one virus? Yes, you can do that. You can choose what antigen to coat, and you can actually use different parts of a virus. And this is very important because some people will use the entire virus to coat, some people use a specific antigen. And so if you find differences in the reactions, it may be that one ELISA kit has more epitopes than another. So that selection of the antigen also determines the specificity and sensitivity of the assay. It's part of the science that goes into assay design. Is the ELISA test kit usually sterilized? The ones which come, yeah, by the time it's coming, it's done in a sterile manner. It comes very nicely wrapped in a thermal pack, and it's supposed to remain sterile. You're not supposed to contaminate it, because if you do, you might have non-specific reactions. I think I'll repeat, or maybe we watch this video first. screen looks quite busy, so let me just share in Anita version. Oh, sorry.
Commercially available ELISA test kits include microplates coated with the antigen of interest and all the necessary reagents. The test should be carried out following the manufacturer's instructions. Dispense the dilution buffer provided by the kit into the wells of the antigen-coated microplate in the proportions suggested by the manufacturer in order to create the proper dilution of the serum samples. Add the positive and negative controls provided by the kit in duplicate. And then add serum samples in the remaining wells. In competitive ELISA kits, where serum from different species may be tested, specific dilution factors are indicated in the instructions, depending on the species under examination. Incubate the microplate at 37 degrees Celsius for the time indicated by the manufacturer to permit the development of an antigen-antibody immunocomplex. After incubation, wash the wells by rinsing with the wash solution provided in the kit. The washing step is usually repeated several times according to the manufacturer's instructions. Prepare the enzyme conjugated antibody by diluting it in the appropriate dilution buffer. This step differs with reference to an indirect ELISA or a competitive ELISA. In indirect ELISA tests, a specific species antibody is conjugated to the enzyme, and the test can be used only for the species indicated by the manufacturer. In contrast, competitive ELISA is based on a monoclonal antibody enzyme conjugate directed against specific epitopes of antigen of interest, allowing for the detection of antibodies in sera collected from all species. Dispense the conjugated antibody into each well. A second incubation is carried out to allow the development of a second immunocomplex. After the incubation, the entire washing procedure is repeated to eliminate the conjugate in excess. Finally, add the substrate and allow for color development for a few minutes in the dark, as recommended by the manufacturer. When the color reaction has finished, add the stop solution provided in the kit and read the results using a spectrophotometer at the wavelength recommended by the manufacturer. Positive results in the indirect ELISA are colored, since the conjugated species-specific antibody binds to the AI antibody present in the positive serum. On the contrary, in competitive ELISA assays, positive results are uncolored. In positive sera, the antigen-antibody complex masks the epitope against which the conjugated monoclonal antibody is directed. The optical density of the color is measured by means of a spectrophotometer. Each manufacturer will specify in their instructions the reference values required for validation of the test and the proper formulas for interpretation of the results obtained. At present, a variety of different ELISA kits are now available on the market, allowing for the detection of the presence of specific antibodies against the nucleoprotein, NP, and the matrix protein, M, of the avian influenza viruses, as well as hemagglutinin 5 and neuraminidase 1.
Okay, so I hope you've seen the assay running. There's no substitute for actually running it, but I think that gives you an idea. I mean, even the pipetting itself is a skill. Sometimes you might pick more than you should if you haven't used a pipette before, but that you gain over time. It's not rocket science. In fact, now there are robotics, there are machines that you just need to put in your sample and your reagents, and everything is done in an automated fashion, from all the pipetting to washing to reading results. There are a lot of bots that are doing that kind of thing. So now we look at lateral flow assays, the next few slides. A lateral flow assay, what we know best, like when you go for HIV testing and do a finger prick, put a drop of your blood into a cassette like this, and then after a few minutes, ranging from 5 to 15 minutes, you get results. That's a lateral flow assay. It is also called a rapid detection test. A lot of you have also used them for pregnancy detection and many other things. So they are liked because they're point of care. They tend to be cheap, and you can use them to detect antibodies, antigens, and sometimes both. And there's also a possibility of multiplex. You can see this one as both IgG and IgM. So that's a sort of multiplexing. And this maybe is detecting NS1, IgG and IgM. NS1 is an antigen, IgG and IgM are antibodies. So this is already a multiplex, able to detect 3 targets in one test. And the fact that you can avail the results within a minute, and the only equipment you need is basically a finger prick needle. You can do this at the clinic, at the bedside, at home, or even in the lab. These are HIV tests, BioLine and Fast Response, which are still in use in the country. You can see the design is different, but the concept is the same. This, you can see the assay structure is exposed completely here, where you put the sample on this white space, and then there's an area here that is loaded with a conjugate and maybe some antibodies, and then the space here on the nitrocellulose membrane, the white area, is where you have your target test. If you're looking for antibodies, it will be an antigen for HIV. And so if this sample has antibodies, it will react and give you a positive like one on this strip. And then the last thing is here is a control. It will basically react with human blood. So it is very general, able to react with human blood, so that, or human sample, so that it can tell you if the sample has crossed all the way to the reservoir. The thing at the end here will absorb any extra sample. So if the controls are not negative, the controls are not showing anything, then your test is invalid. So for all tests, you must have a control for it to be valid. You can see this is positive and this is negative. For the first response, the first one is negative, the second one is positive. And you can see it's a faint positive for HIV1, HIV2 is negative. So the also ability to now, and attempts now to make even more diverse, more multiplexed RDTs. You can see this one here is able to detect eight targets from chikungunya, Lassa virus, malaria, Ebola, Zika, Marburg, and dengue. And the idea here is the malaria pan-plasmodium is able to detect non-falciparum malaria, but you can also specifically look for falciparum malaria. You will learn about this in parasitology next year, the differences, because there are like 5 species of malaria. Falciparum is the most important, but there are others. And even Ebola has different targets, but you can see each of these numbers is coded. So if 1 is positive, you check 1 is chikungunya. If 2 is positive, you check 2 is Lassa. And it's quite interesting because it's also a rapid test. You put in a sample and a buffer, and then it helps quickly give you results for all these pathogens. And this would be very useful for somebody presenting in, say in Uganda right now, there's an Ebola outbreak, and it is in an area which has malaria and maybe even Marburg or Zika. You want to, with this rapid test, to quickly tell you what the person could be having. And then depending on the sensitivity of the assay and the specificity, you can decide whether you need to repeat either all the negatives or all the positives, depending on how specific or how the sensitive the assay is. This is the design, as you can see here. This is the panel, and you start with a hard surface, like you can see in this, the hard surface. This white thing is the hard surface. The test is only this strip here, and this is a cassette. This is plastic covering the strip. So that is the hard surface you can see here. And the place where you put your sample is called a sample pad. There is a conjugate here. A pad here that has a conjugated, say, antibody. And the conjugated antibody, for example, will have something to help you visualize. Usually we use colloidal gold. Colloidal gold will usually be this red color or sometimes blue if it's slightly larger. And so what happens at this sample, you put the sample, you put a buffer, and then as it passes, if this says antigen and the antibody is here, they bind. And then there'll be another, what is it called? And this is usually it will bind to the, what are they called? Both, anything, it's not specific, this conjugate. So when it comes to this test line, the specific binding occurs, and the specific binding could be, say, HIV antigen, if you're looking for antibodies, or HIV antibody if you're looking for antigen, and they will bind to the test line, and you will see the color because the conjugated antibody is now visible here. If there's nothing to bind, it will go ahead and it must bind the control line for it to work, because control line binds everything. And then if there's any excess, it will go into the wick or into the pad that is at the end of the nitrocellulose membrane. So this conjugate is for visualization. This test line is for, that gives it specificity. So if you're looking for an antibody in the sample, you can put an antigen here. If you're looking for an antigen in the sample, you can put an antibody here. If you're looking for an antibody, you can put an antigen. So this test line is what gives you a test specificity. And you can design this even yourselves here in Nairobi. It is possible. You can order this stuff and design a test. What you need to decide is which protein. If you want an antigen, how do you get that antigen? If you want an antibody, how do you produce that antibody? And I encourage you today to look at how to produce monoclonal antibodies and how to produce antigens for pathogens. Okay, so maybe there's a video we can look at before we call it a day. Sorry. So I know this video is fast, so I just paused it for you to look at all the components. And you can see you're starting with the sample part, with the conjugate release part. You have the test line 1, test line 2. This means you have more than one target. You have a control, and then an absorbent part, which absorbs extra sample. Remember, if you are putting here capture antibodies, they could be looking for specific antigen in the sample. Maybe in the sample, you want to see if there's NS1 and say an Ebola protein or another antigen. So they will be captured by these antibodies. Oh, sorry. This is to show you the applications for ELISA, for lateral flow assays. You can see you can test blood, milk, urine, serum, plant material, food, and whatnot. Now, the reason I'm pausing here is so that you can see the blue target here is being captured by the capture antibody on the first test line, and it's already bound to another conjugated antibody. This conjugated antibody has this red colloidal gold conjugated to it, which is what makes it visible. This is what you will see as a line. The color is coming from colloidal gold. Colloidal gold, even if you put it in a test tube, you will see the color. It is visible. And you can see already the antibody is binding to the target, not to the conjugated antibody this time. And so this target is established between the conjugated antibody and the capture antibody, which is on the plate. The same thing to the second test, similar mechanism. And then the last one here is a control line, which is really targeting something that everybody will have in the blood. It could be the RBC, it could be the IgG for humans and all that. So this is really general. It should bind everything. I mean, every sample. If it doesn't bind, then the assay has a problem. Maybe you didn't put your buffer well, or maybe it was not sufficient. You can see for the positive results, the first test line and the second test line may be positive or even one of them, but the control line is positive in both negative and positive results. So the control line, which is usually the farthest from the well, should be positive. If it's not positive, then even if the first two are positive, that test is invalid. So I think we have covered today's work. My aim was to finish before 4, finished well before 4 p.m. But I would like to hear if there are questions at this point, because we have enough time to respond to them. So I'm looking at your chat. Let me. Yeah, I will start from. Yes, so the machine which was reading the sample is called a spectrophotometer. It's basically to read the optical density, how much color is formed. And for most ELISAs, the color is corresponding to the amount of antibody or target antigen in there, except for competitive ELISA. And why is it being washed? You're washing away any excess antibodies. Remember, this is one well, and you're doing so many reactions. So after every reaction, you need to wash away so that whatever is not binding should be washed away. Otherwise, every reaction will be positive. So you're putting in blood. Say you have a well that is coated with an antigen, and then you want to add the sample. And when you add the sample, you clean up, or you incubate for 1 hour at 37 degrees, and then clean up that plate, so that if there's any sample, the sample that is not bound, the antibodies and the sample that are not bound to the plate can be washed off. If you don't wash off, then you're going to have problems with the non-specific binding. For some reason, my okay. So the next comment is on lateral flow assays. Are they the same as rapid detection antibody? Yes, for detecting antibody and antigens, and even now some lateral or rapid detection kits for for what? Nucleic acids. Griffin is asking that the unbound anti-somethings, either antibodies or whatever. I don't understand that. Maybe he was responding to somebody. Are the antibodies on lateral flow assays IgG or IgM? You can choose either. Depends on what you want to find. But IgG tend to be more specific than IgM. So that would be more likely if you're looking for an antigen to use IgG. Without washing the accuracy of the test, I think this is a response. During electives, I observed that they preferred to use serum instead of whole blood. What would be the effect? As I said, whole blood contains a lot of background. So you either use plasma or serum, and serum is better. So you get a lot of noise from RBCs and from other cells in that. And a lot of non-specific binding basically is what I'm calling noise, which means when you look at the background, color will be so much. So you use serum because it has less things there that will cause non-specific binding. Are oral HIV tests a type of lateral flow? Yes, they are. Being used together. Okay. When you wash, how comes the bound antibody and antigen don't wash off? Because they are bound to the cellulose, the plates. Usually they are bound there tightly. There's a membrane there that absorbs them. So you're not washing like everything with a scrubber. And that's why the number of washings determine your sensitivity of the assay. If you wash too much, you wash away everything. If you wash too little, then you don't wash away some of the unbound antibodies and you get non-specific reactions. And that goes when you're developing the assay to test. If I wash 2 times, what do I get? If I wash 4 times, what do I get? If I wash for 3 minutes, what do I get? If I wash for 2 minutes, what do I get? So that is really some of them will be washed off, but some will remain. So you want to make sure that whatever remains is the right thing and you don't wash everything off. Okay. I missed Prof. Oyugi's lecture. That is good. You will have Prof. Oyugi, I think, on Friday next week. Some prefer whole blood. Others prefer serum. So if the sample does not have the antibody or the antibody being tested, the complementary antibody containing the chloride of gold will not be bound. It will only bind to the test, not the control. I mean, to the control, not the test. Yes. So that is the ELISA and lateral flow assays. I think I've responded to all your questions, and I hope you understand ELISA better. As you read around it, some of these things will make more sense, and I will share these slides so that the references are in here. You should be able to take a look as well. And if you have any questions, we are meeting again, I think, next week. If I'm not wrong, I'll be able to answer them. As I said, there's no substitute for actually doing this assay, so if you get a chance, please do them physically. Enjoy your afternoon and your evening. Can rapid tests be used to test for pregnancy? Yes, for many things. They can be used to test many things. Anything that is an antigen or a protein, any protein has been used. Yeah. Okay, thank you very much.